In this moment right now, scattered throughout our universe, there exist objects so strange that they challenge our most fundamental understanding of reality itself. Black holes, regions of space-time where gravity has become so intense that nothing, not even light, can escape, possess a property so counterintuitive that it sounds like science fiction. According to quantum physics, black holes have no hair. This doesn't mean they're bald in any conventional sense. Instead, it reveals one of the most profound and disturbing truths about the universe, that all the complexity, information, and uniqueness that defines everything in our cosmic neighborhood simply vanishes when it encounters a black hole's event horizon. The no-hair theorem represents one of the most elegant yet troubling principles in theoretical physics. It states that black holes can be completely characterized by just three properties: mass, electric charge, and angular momentum spin. Everything else, every detail about the matter that formed the black hole, every piece of information about the stars, planets, or even entire civilizations that might have fallen into it, gets erased from the universe forever. This isn't just theoretical speculation. It has a direct consequence of Einstein's general relativity and quantum mechanics, working together in ways that produce results so bizarre they've kept physicists awake at night for decades. Now, let's begin our journey into the quantum physics of black holes, where we'll discover how these cosmic monsters challenge everything we thought we knew about information, reality, and the fundamental laws that govern our universe. Chapter 1. Hair Discovery and the Peculiar Language of Theoretical Physics. Hair doesn't refer to the familiar strands growing from your scalp, but rather to any distinctive feature or property that makes one object distinguishable from another. When physicists discovered that black holes have no hair, they weren't making an observation about cosmic grooming habits, but revealing one of the most profound and disturbing principles about how information behaves in the universe's most extreme gravitational environments. The concept of hair in physics emerged from attempts to understand what happens to the detailed properties of matter when it collapses to form a black hole. Imagine two identical masses of matter with completely different internal structures. One might be a giant star with complex magnetic fields, rotation patterns, and chemical compositions, while another might be a perfectly uniform sphere of exotic matter. According to the no-hair theorem, after both objects collapse into black holes, they become completely indistinguishable except for three fundamental properties. These three hairless properties that characterize any black hole are mass, electric charge, and angular momentum, spin. Mass determines the strength of the black hole's gravitational field and the size of its event horizon. Electric charge, though typically negligible in realistic astrophysical black holes, affects the electromagnetic fields around the object. Angular momentum describes how fast the black hole rotates, which distorts spacetime around it and affects how matter and energy behave in its vicinity. Dr. John Wheeler, who coined the term black hole and was instrumental in developing the no-hair theorem, explained the concept with characteristic elegance. Black holes have no hair. They are the simplest possible objects in Einstein's universe, characterized by just a few numbers that completely specify their properties. This simplicity stands in stark contrast to the incredible complexity of the objects that might have formed them. The mathematical foundation for the no-hair theorem emerged from detailed studies of Einstein's field equations, the fundamental equations of general relativity that describe how mass and energy curve spacetime. These equations predict that any spherically symmetric, electrically neutral, non-rotating mass that collapses beyond its Schwarzschild radius will form a black hole described completely by its mass parameter. When rotation is added to the system, the mathematics becomes more complex, leading to the Kerr metric that describes rotating black holes. Similarly, adding electric charge produces the Risna-Nordstrom metric for charged black holes, and combining both rotation and charge yields the Kerr-Newman solution. Remarkably, These mathematical solutions suggest that no other hair, no additional parameters or properties is needed to completely specify a black hole's gravitational field. The physical meaning of hairlessness becomes apparent when we consider what happens during gravitational collapse. As matter falls toward the forming black hole, all the complex electromagnetic fields, quantum mechanical properties, and detailed structural information that characterize the original object get smoothed out by the intense gravitational fields. This smoothing process occurs because the event horizon acts like a one-way membrane that prevents information about internal structure from reaching the outside universe. But the no-hair theorem creates an immediate and profound problem when we consider quantum mechanics. In quantum theory, the complete state of any system contains an enormous amount of information: the positions, momenta, spins, and quantum numbers of every particle, along with the complex quantum correlations that exist between different components of the system. This information content is so vast that completely specifying the quantum state of even a small volume of matter would require more information than can be stored in all the computers ever built. According to quantum mechanics, this information can never be destroyed. It can only be transformed, hidden, or redistributed among different parts of a system. This principle, known as unitarity, represents one of the most fundamental assumptions underlying quantum theory. The evolution of quantum systems must be reversible in principle, meaning that if you knew the complete quantum state of the universe at any moment, you could in theory calculate its state at any other time, forward or backward. The collision between the no-hair theorem and quantum unitarity creates what physicists call the information paradox. If black holes really have no hair beyond mass, charge, and spin, then all the quantum information about the matter that formed them appears to be permanently lost. This would violate unitarity and suggest that quantum mechanics breaks down in the presence of strong gravitational fields. The paradox becomes even more acute when we consider Hawking radiation, the theoretical process by which black holes slowly evaporate by emitting quantum particles. Stephen Hawking, as original calculations, suggested that this radiation would be completely random and contain no information about what fell into the black hole. If correct, this would mean that when a black hole finally evaporates completely, all the quantum information it ever absorbed would be destroyed forever. Modern investigations of the no-hair theorem have revealed complexities that weren't apparent in early formulations. For example, certain exotic configurations might possess additional hair in the form of scalar fields or topological properties that don't violate the basic spirit of the theorem while adding new parameters to black hole physics. The study of no-hair theorem has also revealed deep connections between general relativity and thermodynamics. The fact that black holes can be characterized by just a few parameters suggests they might be thermal objects with well-defined temperatures and entropies. This connection led to revolutionary insights about the relationship between gravity, quantum mechanics, and information theory. Experimental tests of the no-hair theorem have become possible with recent observations of black holes using gravitational wave detectors and direct imaging techniques. The Laser Interferometer Gravitational Wave Observatory, LIGO, has detected dozens of black hole mergers. An analysis of these events provides tests of whether the merging objects really behave like the simple hairless black holes predicted by general relativity. The Event Horizon Telescope has direct images of the supermassive black holes in M87 and our own galaxy provide additional tests of the no-hair theorem. These observations reveal whether real black holes possess the simple geometries predicted by the Kerr metric or exhibit additional complexities that might constitute hair in the technical sense. Quantum field theory in curved spacetime has revealed that the concept of no hair might be more subtle than originally thought. Quantum fluctuations near black holes can create complex field configurations that carry information while still being consistent with the basic framework of general relativity. String theory and other approaches to quantum gravity suggest that black holes might possess microscopic hair in the form of quantum degrees of freedom that are uncaptured by classical general relativity. These quantum hair might provide mechanisms for information storage and retrieval that resolve the information paradox while maintaining the essential simplicity of black hole physics. The holographic principle offers another perspective on black hole hair, suggesting that all information about a black hole's interior might be encoded on its two-dimensional event horizon surface. From this viewpoint, black holes do contain hair, but it's written in a quantum language so sophisticated that we're only beginning to learn how to read it. Recent developments in a DSCFT correspondence, a mathematical framework that relates gravity theories to quantum field theories, have provided new ways to think about black hole information and the meaning of no hair. These advances suggest that the information paradox might be resolved through quantum mechanical effects that preserve information while maintaining the apparent simplicity of black hole exteriors. The philosophical implications of the no-hair theorem extend beyond technical physics to fundamental questions about the nature of individuality, information, and identity. If complex systems can be reduced to just three numbers when they encounter black holes, what does this tell us about the ultimate nature of complexity and information in our universe? Dr. Samir Mathur from Ohio State University reflects on the deeper meaning. The no-hair theorem forces us to confront fundamental questions about what information really is and whether complexity can truly be reduced to simplicity. Understanding black hole hair, or the lack thereof, may be the key to understanding how quantum mechanics and gravity work together to create reality. The discovery that black holes have no hair revealed that the universe contains objects of unprecedented simplicity that emerge from the collapse of arbitrarily complex systems. This simplicity creates profound puzzles about information conservation while pointing toward revolutionary insights about the fundamental nature of spacetime, quantum mechanics, and the deep connections between gravity and information theory. Understanding what physicists mean by hair in the context of black holes opens the door to exploring how these cosmic objects challenge our most basic assumptions about how information behaves in the universe, setting the stage for examining the profound conflicts between general relativity and quantum mechanics that continue to drive cutting-edge research in theoretical physics. Chapter 2: Einstein's Legacy. The story of why black holes have no hair begins with Albert Einstein's revolutionary theory of general relativity, published in 1915, which transformed our understanding of gravity from a force acting between objects to a curvature in the fabric of spacetime itself. Einstein's field equations provided the mathematical framework that would eventually predict the existence of black holes and establish the theoretical foundation for understanding why these cosmic objects possess such remarkably simple properties despite their exotic nature. Einstein's key insight was recognizing that massive objects don't simply attract other objects through some mysterious force, but actually warp the geometry of space and time around them. This warping creates what we experience as gravitational effects, with objects following the straightest possible paths through curved spacetime, paths that appear curved when viewed from our everyday three-dimensional perspective. The mathematical elegance of Einstein's field equations belies their incredible complexity. These 10-coupled, nonlinear partial differential equations relate the curvature of spacetime, described by the Einstein tensor, to the energy and matter content of space, described by the stress-energy tensor. Finding exact solutions to these equations proved extraordinarily challenging, requiring mathematical techniques that pushed the boundaries of what was possible in early 20th century physics. Dr. Kip Thorne from Caltech, who won the Nobel Prize for his contributions to gravitational wave detection, explains Einstein's achievement. General relativity revealed that space and time are not the rigid stage on which physics plays out, but dynamic participants in cosmic drama. Einstein showed us that matter tells space-time how to curve, and curved space-time tells matter how to move. The first exact solution to Einstein's field equations was discovered by Kerr and Schwarzschild in 1916, just months after Einstein published his theory, and tragically just days before Schwarzschild died of an illness contracted on the Russian front during World War I. The Schwarzschild solution describes the spacetime geometry around a spherically symmetric, non-rotating massive object and predicted the existence of a critical radius, later called the Schwarzschild radius, where the curvature of spacetime becomes so extreme that a boundary forms beyond which nothing can escape. Initially, physicists, including Einstein himself, resisted the idea that the Schwarzschild solution could describe real physical objects. The mathematical predictions seemed too extreme. Infinite curvature at the center, a boundary in spacetime that could trap light itself, and regions where the normal notion of cause and effect might break down. These features appeared to violate physical intuition so dramatically that they were dismissed as mathematical artifacts rather than predictions about real cosmic objects. The mathematical structure of the Schwarzschild solution revealed why collapsed objects would have no hair in the technical sense. The solution depends only on one parameter, the mass of the central object, which completely determines the geometry of spacetime around it. No matter how complex the original object might have been, its external gravitational field would always be described by the simple, spherically symmetric solution. Roy Kerr's 1963 discovery of the rotating black hole solution added angular momentum as a second parameter that could characterize collapsed objects. The Kerr metric describes spacetime around spinning black holes and revealed how rotation distorts the simple spherical symmetry of the Schwarzschild solution, creating effects like frame dragging, where the rotation of the central mass drags spacetime around with it. The addition of electric charge through the Reissner-Nordstrom solution and its rotating generalization, the Kerr-Newman metric, completed the mathematical framework for describing black holes with the three fundamental parameters: mass, charge, and angular momentum. Remarkably, decades of searching for additional parameters that might characterize black holes have failed to find any beyond these three, providing strong support for the no-hair theorem. Einstein's field equations not only predicted the existence of black holes, but also established the mathematical framework for understanding their thermodynamic properties. The equations suggest that black holes should behave like thermal objects with well-defined temperatures and entropies, connections that weren't fully appreciated until decades later when Stephen Hawking discovered that quantum effects cause black holes to radiate. The Einstein-Hilbert action, which provides the fundamental principle underlying general relativity, establishes a deep connection between geometry and physics that helps explain why black holes possess such simple properties. The action principle requires that spacetime evolves along paths that minimize the total curvature, leading naturally to solutions with maximal symmetry and minimal complexity. General relativity's prediction of gravitational time dilation becomes extreme near black holes, with time appearing to slow down dramatically as observed from distant locations. This effect, combined with the one-way nature of the event horizon, provides a physical mechanism for understanding how complex information about infalling matter becomes hidden from external observers, contributing to the apparent loss of hair. The mathematical framework of differential geometry that underlies general relativity provides powerful tools for analyzing black hole spacetimes and understanding their properties. Concepts like geodesics, curvature tensors, and spacetime topology become essential for describing how matter and energy behave in the extreme gravitational environments around black holes. Einstein's equivalence principle, the observation that gravitational and inertial effects are locally indistinguishable, provides deep insights into black hole physics. Near the event horizon, freely falling observers experience no local gravitational forces, yet their global situation differs dramatically from observers far from the black hole. illustrating how general relativity reconciles local and global perspectives on spacetime structure. The field equations also predict the existence of gravitational waves, ripples in spacetime itself that propagate at light speed and carry information about accelerating masses. These waves provide new windows into black hole physics and offer experimental tests of general relativity's predictions about black hole properties and the validity of the no-hair theorem. Modern extensions of Einstein's theory have explored whether additional fields or higher dimensional effects might add hair to black holes while remaining consistent with general relativity. These investigations have revealed that certain exotic matter configurations might create observable deviations from the simple three-parameter description, though such deviations appear to be extremely subtle. The mathematical elegance of Einstein's field equations continues to inspire theoretical work on unified theories that might reconcile general relativity with quantum mechanics. Understanding how quantum effects modify the classical predictions of general relativity near black holes represents one of the most important unsolved problems in theoretical physics. Numerical relativity, the use of powerful computers to solve Einstein's equations in complex dynamic situations, has revolutionized our ability to study black hole physics. These computational techniques have enabled detailed studies of black hole mergers and provided insights into how the no-hair theorem applies to highly dynamic, non-equilibrium situations. The holographic principle, one of the most important developments in modern theoretical physics, emerged partly from studying the implications of Einstein's field equations for black hole physics. This principle suggests that all information in a volume of space can be encoded on its boundary surface, with profound implications for understanding how general relativity and quantum mechanics might be unified. Recent observations of black holes through gravitational wave astronomy and direct imaging have provided unprecedented tests of Einstein's predictions about black hole properties. These observations confirm that real black holes behave remarkably like the simple objects described by the classical solutions to Einstein's field equations. Dr. Roger Penrose, who shared the 2020 Nobel Prize for his contributions to black hole physics, reflects on Einstein as enduring legacy. Einstein's field equations revealed that spacetime itself is a dynamic, malleable medium that responds to matter and energy. This insight provided the foundation for understanding black holes as inevitable consequences of gravitational collapse, rather than exotic speculations. Einstein's legacy in black hole physics extends far beyond the original field equations to encompass a worldview that sees space, time, matter, and energy as interconnected aspects of a unified geometrical structure. This perspective continues to guide research into quantum gravity and the fundamental nature of spacetime. The mathematical framework established by Einstein's general relativity provides the foundation for understanding why black holes have no hair, while simultaneously creating the conceptual puzzles that arise when quantum mechanics is applied to curved spacetime. Einstein's equations predicted the existence of objects so simple yet so strange that they continue to challenge our understanding of reality itself. Understanding Einstein's legacy reveals how mathematical beauty and physical insight combine to predict the existence of cosmic objects that would eventually revolutionize our understanding of information, quantum mechanics, and the fundamental nature of reality, setting the stage for exploring how event horizons create the boundaries that give black holes their mysteriously simple properties. Chapter 3. Event Horizons. The event horizon represents one of the most profound and mysterious boundaries in all of physics, a spherical surface surrounding every black hole beyond which nothing, not even light itself, can ever escape back to the outside universe. Understanding event horizons is crucial for grasping why black holes have no hair, because these cosmic boundaries create a one-way membrane that forever separates the interior of a black hole from the external universe, effectively erasing all information about what lies beyond from any outside observer's perspective. The physics of event horizons emerges directly from Einstein's general relativity, which predicts that sufficiently massive objects will curve space-time so severely that they create regions from which escape becomes impossible. The critical size at which this occurs is called the Schwarzschild radius, named after Kerr and Schwarzschild, who first derived the mathematical solution describing space-time around spherically symmetric masses. For a black hole with the mass of our Sun, the Schwarzschild radius equals approximately 3 kilometers. Earth would have a Schwarzschild radius of just 9 millimeters, while a supermassive black hole containing 1 billion solar masses would have an event horizon with a radius larger than our solar system. These radii define the locations of event horizons, spherical surfaces where the escape velocity equals the speed of light. Dr. Kip Thorne, whose work on black hole physics earned him a Nobel Prize, explains the profound nature of event horizons. The event horizon isn't a physical surface you could touch or see. It is a boundary in space-time itself, a point of no return where the curvature becomes so extreme that all paths lead inward. Once you cross this boundary, your future light cone, the set of all events you could possibly influence, lies entirely within the black hole. From the perspective of someone falling through an event horizon, the crossing appears unremarkable. General relativity's equivalence principle ensures that freely falling observers experience no local gravitational forces. So a person crossing an event horizon wouldn't feel anything special happening at that moment. The space-time curvature that creates the horizon affects the global structure of their possible futures. But locally, physics continues to operate normally. However, from the perspective of distant observers, the event horizon creates dramatic effects due to gravitational time dilation. As objects approach the event horizon, time appears to slow down relative to distant clocks. Light from infalling objects becomes increasingly redshifted, growing dimmer and redder until it fades beyond detection. To outside observers, objects appear to freeze at the event horizon, their images slowly fading to black as the light becomes too redshifted to observe. This dramatic difference in perspectives between falling and distant observers creates what physicists call the black hole complementarity principle. The same events can be described in two seemingly contradictory ways. Infalling observers pass through the event horizon and experience the interior of the black hole, while distant observers see everything remain outside the horizon, gradually fading from view as it becomes thermalized into Hawking radiation. The mathematics of event horizons reveals why black holes have no hair from the perspective of external observers. Once information crosses the event horizon, it becomes causally disconnected from the outside universe. No signal or influence can travel from inside the horizon to affect anything outside. This causal disconnection means that the detailed properties of matter inside the black hole cannot influence the external gravitational field or electromagnetic environment. Rotating black holes possess more complex event horizon structures described by the Kerr metric. These black holes have two horizons, an outer event horizon beyond which escape is impossible, and an inner Cauchy horizon where the predictable evolution of space-time may break down. Between these horizons lies a region called the ergosphere, where space-time itself is dragged around by the black hole's rotation. The area theorem proven by Stephen Hawking in the 1970s states that the total area of event horizons can never decrease in any classical process. This theorem has profound implications for black hole physics because it connects the geometry of event horizons to thermodynamic concepts like entropy. The area theorem suggests that black holes possess entropy proportional to their surface area rather than their volume, a relationship that points toward deep connections between gravity and information theory. Charged black holes, described by the Racine and Nordstrom metric, can possess two event horizons when the charge is less than a critical value, or no event horizon at all when the charge exceeds this critical threshold. Naked singularities, gravitational collapse events that do inform event horizons, would violate cosmic censorship and potentially allow information to escape from regions of infinite space-time curvature. The information paradox emerges directly from the properties of event horizons combined with quantum mechanical principles. If event horizons permanently prevent information from escaping black holes, and if black holes eventually evaporate through Hawking radiation, then quantum information would be destroyed when black holes disappear. This apparent destruction violates the fundamental quantum mechanical principle of unitarity. Recent theoretical developments have suggested that event horizons might be more complex than originally thought when quantum mechanical effects are included. Some theories propose that the event horizon might not be a perfectly sharp boundary, but rather a stretched horizon with a finite thickness where quantum effects become important. The holographic principle suggests that all information about a black hole's interior might be encoded on its event horizon surface. From this perspective, the event horizon isn't just a boundary that prevents information from escaping. It is a two-dimensional repository that contains all information about the three-dimensional interior in a highly encoded form. Quantum entanglement between particles inside and outside black holes creates subtle correlations that might allow information to escape without violating the causal structure imposed by event horizons. These quantum correlations operate through non-local connections that don't require faster-than-light communication, but still preserve information about the black hole's interior. The firewall paradox, proposed by physicists at UC Santa Barbara, suggests that event horizons might be locations of extremely high energy density where quantum effects create a firewall of radiation that would destroy anything attempting to cross the boundary. This paradox highlights ongoing debates about what really happens at event horizons when quantum mechanics is fully incorporated. Observational tests of event horizon physics have become possible with recent advances in astronomical technology. The Event Horizon Telescope has directly imaged the shadows of supermassive black holes, revealing the photospheres that surround event horizons and providing tests of general relativity as predictions about black hole geometry. Gravitational wave observations from merging black holes provide additional insights into event horizon physics by revealing how these boundaries behave during highly dynamic processes. The gravitational waves carry information about the final moments before black holes merge and the properties of the event horizons that result from these cosmic collisions. The thermodynamic properties of event horizons connect black hole physics to fundamental questions about the nature of space, time, and information. The Bekenstein-Hawking entropy formula, which relates black hole entropy to event horizon area, suggests that spacetime itself might have microscopic degrees of freedom that account for black hole thermodynamic behavior. Future theoretical developments may reveal that event horizons are emergent phenomena that arise from more fundamental quantum gravitational effects. String theory and other approaches to quantum gravity suggest that the smooth spacetime geometry predicted by general relativity might be an approximation that breaks down near event horizons. Dr. Leonard Susskind from Stanford University reflects on the mysteries of event horizons. Event horizons represent the ultimate information processing boundary. They separate what can be known from what must remain forever hidden. Understanding how quantum mechanics operates at these boundaries may be the key to unifying gravity with quantum field theory. The study of event horizons continues to drive cutting-edge research in theoretical physics, from investigations of quantum gravity to explorations of how information and entropy behave in curved spacetime. These boundaries create the fundamental interface where general relativity and quantum mechanics meet, often in ways that challenge our basic assumptions about causality, information, and the nature of physical reality. Event horizons transform black holes from simple massive objects into cosmic information processors that challenge our understanding of how quantum mechanics and general relativity work together, creating the boundaries that give black holes their remarkably simple external properties, while potentially harboring infinitely complex internal structures that remain forever hidden from outside observation. Chapter 4. Information Paradox. The information paradox represents the most profound challenge to our understanding of fundamental physics, posed by black holes creating a seemingly irreconcilable conflict between general relativity and quantum mechanics. That strikes at the heart of how information behaves in our universe. This paradox emerges when we combine Einstein's prediction that black holes have no hair with quantum mechanics' fundamental requirement that information can never truly be destroyed, only transformed or redistributed among different parts of a system. In quantum mechanics, the complete description of any system requires specifying its quantum state, which contains an enormous amount of information about the positions, momenta, spins, and quantum correlations of every particle. This information content grows exponentially with the number of particles. A system with just 300 particles has more possible quantum states than there are atoms in the observable universe. The principle of unitarity, which governs how quantum systems evolve, demands that this information be preserved throughout any physical process. Dr. Stephen Hawking's discovery in the 1970s that black holes emit thermal radiation created the modern form of the information paradox. Hawking's calculations showed that black holes behave like perfect thermal objects, radiating particles with a temperature inversely proportional to their mass. This Hawking radiation carries energy away from black holes, causing them to slowly shrink and eventually evaporate completely over timescales that exceed the current age of the universe for stellar mass black holes. The paradox arises because Hawking's original calculations suggested that the radiation emitted by black holes is completely random and thermal, containing no information about what originally fell into the black hole. If this radiation is truly random, then all the quantum information about the matter that formed the black hole and everything that subsequently fell into it would be destroyed when the black hole finally evaporates completely. Such information destruction would violate unitarity, one of the most fundamental principles of quantum mechanics. Unitary evolution means that if you knew the complete quantum state of the universe at any moment, you could in principle calculate its state at any other time, either forward or backward. Information destruction would make this reversible evolution impossible, fundamentally altering the mathematical framework that underlies quantum mechanics. Dr. Leonard Susskind from Stanford University, who has spent decades working on the information paradox, explains its significance. The information paradox isn't just a technical problem in black hole physics. It is a crisis that threatens the logical consistency of quantum mechanics and general relativity. If information can truly be destroyed, then the universe operates according to fundamentally different principles than we thought possible. The paradox becomes even more acute when we consider the page time, the moment when a black hole has radiated away half of its original mass through Hawking radiation. Before this time, the black hole is larger and could potentially store all information about what fell into it. After this time, the black hole becomes smaller than would be needed to store all that information. Yet it continues to radiate apparently random thermal radiation until it disappears entirely. Quantum error correction theory provides a framework for understanding why information destruction poses such fundamental problems. In quantum systems, information can be encoded redundantly across multiple particles in ways that make it recoverable, even when some particles are lost or corrupted. But if black holes truly destroy information, they would represent a type of error that no quantum error correction scheme could fix. The holographic principle emerged partly as an attempt to resolve the information paradox, by suggesting that all information about a black hole's interior is encoded on its two-dimensional event horizon surface. This encoding would be so sophisticated that information appears to be lost to outside observers, who lack the ability to decode the quantum correlations stored on the horizon surface. Recent developments in quantum entanglement theory have provided new perspectives on the information paradox. Some physicists propose that information might escape from black holes through subtle quantum correlations between Hawking radiation particles and the black hole's internal degrees of freedom. These correlations would be undetectable to classical observers, but could preserve quantum information in a way that maintains unitarity. The ADCC correspondence, a mathematical framework that relates gravity in curved spacetime to quantum field theory on the boundary of that space, has provided powerful tools for studying the information paradox. In a DSCFT, the formation and evaporation of black holes can be described using quantum field theory, where unitarity is manifest and information is clearly conserved. String theory offers another perspective on information conservation by suggesting that black holes might be composed of fundamental strings rather than point particles. In string theory, black hole formation and evaporation can be described as rearrangements of string configurations that preserve information while appearing to create and destroy black holes from the perspective of low-energy observers. The black hole complementarity principle attempts to resolve the paradox by suggesting that different observers can have different but equally valid descriptions of the same physical events. Infalling observers see information cross the event horizon and fall toward the singularity, while distant observers see the same information encoded in Hawking radiation. Both descriptions would be correct within their respective reference frames. Quantum entanglement between the interior and exterior of black holes creates non-local correlations that might provide mechanisms for information retrieval that do not violate causality. These correlations operate through quantum mechanical effects that allow information about the black hole's interior to influence the statistical properties of Hawking radiation without requiring faster-than-light communication. The firewall paradox, proposed in 2012, highlighted additional complications in resolving the information paradox. If information is to escape from black holes through entanglement between interior and exterior states, then the event horizon might become a high-energy firewall that destroys anything attempting to cross it, contradicting general relativity's prediction that event horizons should appear normal to freely falling observers. Experimental approaches to testing the information paradox remain limited by the incredibly long timescales involved in black hole evaporation and the weakness of Hawking radiation for stellar mass black holes. However, analog black hole systems created in laboratory settings might provide insights into how quantum information behaves in curved spacetime geometries. The recent calculations suggesting that Hawking radiation might not be perfectly thermal, but instead carry subtle correlations that encode information about the black hole's interior have reinvigorated research into the information paradox. These calculations suggest that information might escape very slowly throughout the black hole's lifetime rather than being released suddenly at the end of the evaporation process. Computational approaches to studying the information paradox have revealed that seemingly simple questions about information conservation in black holes require understanding some of the most complex aspects of quantum many-body physics. The mathematical techniques needed to fully resolve the paradox might require advances in our understanding of quantum complexity and quantum error correction. The philosophical implications of the information paradox extend beyond technical physics to questions about the nature of reality, determinism, and the fundamental limits of knowledge. If information can truly be destroyed, it would have profound consequences for everything from the arrow of time to the relationship between consciousness and physical law. Recent work on quantum gravity has suggested that the information paradox might be resolved by recognizing that space-time itself emerges from more fundamental quantum information processing. From this perspective, black holes do not destroy information, but rather reorganize it in ways that reveal the quantum mechanical nature of space-time geometry. Dr. John Preskill from Caltech, who has contributed extensively to quantum information theory, reflects on the paradox as broader significance. The information paradox forces us to confront the deepest questions about how quantum mechanics and gravity work together. Resolving it may require revolutionary changes in our understanding of space, time, and information that will transform physics in ways we can barely imagine. The information paradox continues to drive cutting-edge research at the intersection of quantum mechanics, general relativity, and information theory. The resolution of this paradox may provide the key insights needed to develop a complete theory of quantum gravity that unifies our understanding of the fundamental forces and reveals the true nature of space-time and information in our universe. Understanding the information paradox reveals how black holes challenge our most basic assumptions about how information behaves in physical systems, creating conflicts between our most successful theories that point toward revolutionary new physics that may transform our understanding of reality itself. Chapter 5. Hawking Radiation. Stephen Hawking's discovery in 1974 that black holes emit radiation fundamentally transformed our understanding of these cosmic objects from eternal information-destroying monsters into dynamic evolving systems that connect quantum mechanics, thermodynamics, and gravity in ways that challenge our deepest assumptions about the nature of reality. Hawking radiation emerges from quantum mechanical effects near black hole event horizons, revealing that even the most extreme gravitational environments in the universe cannot completely suppress the quantum vacuum fluctuations that permeate all of space. The theoretical foundation for Hawking radiation lies in quantum field theory applied to curved space-time geometries. In the quantum mechanical description of reality, even empty space teems with virtual particle pairs that spontaneously appear and disappear on timescales so brief that they normally remain undetectable. These virtual particles represent quantum fluctuations of the fundamental fields that fill all of space, creating a sea of ephemeral matter and antimatter pairs that continuously pop into and out of existence. Near a black hole's event horizon, these quantum vacuum fluctuations encounter the extreme curvature of spacetime in ways that can transform virtual particles into real observable radiation. When a virtual particle pair appears near the event horizon, one member of the pair might fall into the black hole while the other escapes to infinity. The escaped particle becomes real Hawking radiation, while the particle that falls into the black hole carries negative energy that slightly reduces the black hole's total mass. Dr. Stephen Hawking's original calculation of this process revealed that black holes emit thermal radiation with a temperature inversely proportional to their mass. For a black hole with the mass of our Sun, this Hawking temperature equals approximately 60 nanokelvins, far colder than the cosmic microwave background radiation that permeates the universe. Only primordial black holes with masses less than the Moon would have Hawking temperatures exceeding room temperature. The mathematical derivation of Hawking radiation requires sophisticated techniques from quantum field theory in curved spacetime, including concepts like Bogoliubov transformations that describe how quantum states defined in different regions of curved spacetime relate to each other. These calculations reveal that what appears as empty vacuum to observers far from a black hole looks like a thermal bath of particles to observers near the event horizon. The spectrum of Hawking radiation follows a perfect black-body distribution, meaning that black holes behave like ideal thermal objects with well-defined temperatures. This thermal nature initially suggested that Hawking radiation carries no information about what fell into the black hole, creating the information paradox that has dominated black hole physics for decades. The power radiated by black holes through the Hawking process is incredibly small for astrophysical black holes. A solar mass black hole radiates energy at a rate of about 10 to 28 watts, far less than the power radiated by a single human hair exposed to room temperature infrared radiation. This tiny power output means that stellar mass black holes would require times longer than 1067 years to evaporate completely, far exceeding the current age of the universe. However, smaller black holes radiate much more intensely. The Hawking temperature and radiation rates scale inversely with mass, so hypothetical microscopic black holes would radiate enormous amounts of energy in very brief periods. A black hole with the mass of a mountain would explode with the energy of millions of hydrogen bombs within a fraction of a second. The thermodynamic properties revealed by Hawking radiation connect black hole physics to fundamental principles governing all thermal systems. The Bekenstein-Hawking entropy formula shows that black hole entropy equals 1/4 of the event horizon area measured in Planck units, suggesting that black holes contain enormous numbers of microscopic degrees of freedom that account for their thermal behavior. This connection between black hole area and entropy implies that black holes represent the maximum entropy that can be contained within any given volume of space, a principle that has profound implications for cosmology, quantum gravity, and the fundamental limits of information storage in physical systems. The discovery of Hawking radiation also revealed that black holes have finite lifetimes rather than persisting forever as originally thought. As black holes radiate energy, they lose mass and shrink, causing their Hawking temperature to increase and their evaporation rate to accelerate. This runaway process culminates in explosive evaporation when black holes reach microscopic sizes. Recent theoretical developments have suggested that Hawking radiation might not be perfectly thermal, but could carry subtle correlations that encode information about the black hole's interior. These correlations would be incredibly small and would only become apparent after the black hole had radiated away most of its mass, but they might provide a mechanism for information retrieval that preserves quantum mechanical unitarity. The page curve describes how the entropy of Hawking radiation should evolve during black hole evaporation if information is conserved. Initially, the radiation entropy increases as more thermal radiation is emitted, but after the page time, when the black hole has lost half its mass, the radiation entropy should decrease as information begins to emerge in the correlations between early and late radiation. Analog black hole systems created in laboratory settings have provided experimental tests of some aspects of Hawking radiation theory. These systems use sound waves in moving fluids or light waves in optical media to create effective event horizons where some features of Hawking radiation can be observed and studied directly. The holographic principle suggests that Hawking radiation might be understood as information flowing from the black hole's interior to its boundary surface, where it becomes encoded in the quantum correlations that define the black hole's microscopic state. From this perspective, Hawking radiation represents a gradual release of information rather than its destruction. String theory provides microscopic models of black holes that suggest Hawking radiation emerges from the quantum mechanical properties of the fundamental strings that comprise black holes. These models reveal that black holes contain vast numbers of microscopic degrees of freedom that can account for both their entropy and their ability to emit thermal radiation while potentially preserving information. The ADS-CFT correspondence has enabled exact calculations of Hawking radiation in certain mathematical models where black holes in curved spacetime correspond to thermal states in quantum field theories. These calculations confirm that Hawking radiation preserves information while appearing thermal to observers who cannot access the complete quantum state. Gravitational wave observations of black hole mergers have provided indirect tests of black hole thermodynamic properties by measuring how much energy is radiated during these collisions. while direct observation of Hawking radiation remains beyond current technology. These measurements confirm other predictions of black hole thermodynamics. The quantum entanglement structure of Hawking radiation reveals deep connections between black hole physics and quantum information theory. Understanding how entanglement propagates through Hawking radiation might provide insights into how quantum information escapes from black holes, while respecting both general relativity and quantum mechanical principles. Future observations using gravitational wave detectors might detect signatures of Hawking radiation from primordial black holes if these objects exist and are evaporating in the current universe. Such observations would provide direct tests of Hawking's theoretical predictions and insights into black hole quantum mechanics. The study of Hawking radiation in higher dimensional spacetimes and modified gravity theories has revealed how the basic process depends on the fundamental structure of spacetime and the number of dimensions. These investigations provide insights into how Hawking radiation might behave in theories of quantum gravity that extend beyond general relativity. Dr. Dome Page, who made fundamental contributions to black hole thermodynamics, reflects on the significance of Hawking radiation. Hawking's discovery that black holes radiate revealed deep connections between gravity thermodynamics and quantum mechanics that we're still trying to fully understand. This radiation transformed our view of black holes from static objects to dynamic systems that evolve and eventually disappear. Hawking radiation demonstrates that black holes are not the information-destroying monsters they initially appeared to be, but rather complex quantum mechanical systems that process information in ways we're only beginning to understand. The thermal nature of this radiation creates the information paradox while simultaneously pointing toward potential solutions that preserve quantum mechanical unitarity. Understanding Hawking radiation reveals how quantum mechanical effects operate in curved spacetime while connecting black hole physics to fundamental questions about thermodynamics, information theory, and the ultimate fate of information in our universe, providing crucial insights for developing theories of quantum gravity that unify general relativity and quantum mechanics.